Good morning, everyone. So we are actually from the beautiful Detroit, and actually joining us today we have some colleagues back in Detroit, in our Wayne State University campus in Detroit. So essentially what we're looking at is the paradigm change for the road transportation, essentially moving from the traditional single vehicle-based operation to a connected automated vehicle network operation setting. So there have been many canonical applications explored in this context, including active safety and network fuel economy optimization. But there's one important area that has not been well explored, which is public safety. So today we're going to focus on this as one canonical application for connected and automated vehicles. So let's hear our police chief, saying how this relates to their mission.
Camera-based surveillance provides visual information that's critical for detecting, reducing, and responding to public safety threats. But existing systems present different camera views as separate ones. This makes it difficult to comprehend rich, dynamic visual information, especially when the number of cameras is larger or an emergency response. It would be great if we could combine separate camera views into a natural-looking 3D world that can be navigated and observed, as if walking or flying, to address the blind zones and limited view angles of infrastructure-mounted cameras. It would also help to combine cameras mounted on police vehicles with fixed infrastructure-mounted cameras. Network 3D vision can significantly enhance our capabilities of managing emergencies, and we're pleased to collaborate with our faculty colleagues in the research and deployment of these systems. Besides public safety surveillance, another challenge today is driving safely in an emergency. In the U.S. alone, 35 to 40% of all police pursuits end in a collision, killing more than one person a day, including police and innocent bystanders. To reduce driving accidents and improve the safety and effectiveness of emergency responses, it's crucial to develop network 3D vision systems that combine views from vehicle and infrastructure mounted cameras, like those on traffic lights, so that in-place traffic, road, and pedestrian information can be provided to police and civilian drivers in a natural manner. In 1921, Detroit police were the first in the world to deploy radios in patrol vehicles. Today, we're proud to be on the cutting edge of technology again, collaborating with researchers to develop and deploy network 3D vision systems for public safety and connected and automated vehicles in general.
So hopefully through our chief's testimony, you get a sense on how the wireless network 3D vision could help their mission. So today we're going to show just one example of that, which is 3D mapping. So basically, we have our police vehicles running in Detroit over there. We're going to stream that video stream live into the demo site in a real-time 3D environment. So now let's go to the demo site. Can we show the raw video? Yeah, so here's actually what a police officer in the patrol car could see. But usually for folks in the control center, then it's pretty difficult to understand what's exactly happening there. So then what we can do is first to actually integrate this real-time view into a high-fidelity 3D world of the campus. So for example, can we move to the tagged view? So for example, you can actually kind of embed this real-time stream into the 3D campus world so that the 3D model can give you actually the broad context about what the officer can see in field. Now, if we go one step further, you can actually embed what the officer is seeing into the 3D model itself so that it's like for folks in the control center, it's like you are actually there in the field. You can see exactly what's happening over there. So we still have a little bit delay in networking, so that's why there's a need for actually networking research, which will come back a little bit later in a few minutes. So it's making turns, which this is a scenario where it's actually a little bit challenging to do 3D embedding. So once we get to the street movement, the effect is going to be much better. So essentially, the idea is that with the integration of the real-time view into a 3D world, this would essentially make it much easier to navigate through the sim so that you can have better situation awareness, therefore be more effective in law enforcement. Now, so if you look into the future, there's going to be a continuous evolution of different applications in this direction. For example, one area we're currently looking at is how to move from the 3D mapping we just showed to a really real-time collaborative 3D vision. For example, where you could have different streams coming from different cameras, from the infrastructure or vehicle-mounted cameras, and then we can actually integrate those camera data into a 3D world in real time that can be navigated, or you can also even include some automated detection and tracking capabilities into this system. Now, if we go beyond public safety, we can also look at cases where we actually take the 3D vision data to enable better control of the connected vehicles. So therefore, there's a question of how do we actually enable this smooth evolution of applications and networks in connected and automated vehicles. Now, if you look at traditionally how the innovation happens, usually we do research and development in the lab with 1 or 2 cars, and then usually you just deploy those develop features in field in a large traffic flow, and then they would actually work pretty well. But now when we look at connected vehicles, then the drawback of this model is that the lab test actually doesn't capture the network impact on the vehicle operation itself. So therefore, we see the need for of the transition from that model to a new model of innovation where you can actually integrate real-time research and development experiments in actual real-world deployments of vehicles. So basically, the actual applications and research experiments happen at the same time in real world. So that's kind of another aspect we have been working on. Toward the end, we have actually developed the system so that we can actually we have deployed our innovation platforms into our patrol vehicles so that on one hand, you can actually run real-world applications for the public safety, as we have shown. But in the meantime, we can use the same deployment to support research experiments. So today, we're going to show part of that. For example, we're going to show how we can integrate the real-world deployment with large-scale simulation in the cloud to enable at-scale emulation of connected and automated vehicles. So just let's go to the actual emulation part. So here we have essentially a simulation running that has many vehicles, but two of those vehicles are mapped with the real-world vehicles so that we can actually use the real-world measurement data to drive the simulation. For example, if we can go to the vehicle state sensing? Yeah. So basically, you can get real-time data from the vehicle, and using this data, you can actually drive the emulation. For example, you can use this data to drive the modeling of the simulation itself in terms of, for example, the driver reaction time, which is quite important in the connected vehicle emulation. And then once you have this high fidelity emulation model, you can actually evaluate different protocols. For example, here we are showing the emulation results of 2 inter-vehicle communication protocols. One is CSMA, which is a foundation for the current DSRC implementation. That is the foundation for the current inter-vehicle communication standards. The other protocol is VPROX, which is a protocol specifically designed for enabling predictable communication reliability between vehicles. So VPROX is a result of our NSF-funded projects. Now, in these 2 figures here, you can see the estimation error in inter-vehicle distance and vehicle speed using different protocols. Now, as you can see here, if we use the CSMA-based approach, the estimation error tends to be very high. For example, the inter-vehicle distance estimation error could be more than 3 meters, which could mean actual accidents
in practice. So on the other hand, if you look at the solution of VPERKs, because the communication reliability is very high, which leads to very low estimation error, and the estimation error tends to be negligible, as you can see here. So with this, essentially, you can enable, using the emulation system, as you can see here, we can enable high fidelity evaluation of different inter-vehicle communication solutions, which would help us make the right decision on choosing the right protocol for enabling enabling the vision of connected and automated vehicle. So in general, the emulation system allows us to evaluate new solutions, new ideas in high fidelity settings, which would help facilitate the adoption and deployment of new solutions, therefore enabling faster and smoother evolution of the technologies of connected and automated vehicles.
So with that, we hope to have shared with you on one hand, the potential impact of connected and automated vehicles on public safety. But in the meantime, think about how we can enable a new way of innovation in connected and automated vehicles, where we can actually integrate real-world deployment with research experiment at the same time. So before I conclude, I just want to mention that actually back in 1921, as our chief mentioned, the Detroit Police was the first police division to deploy radios in cars, in patrol cars. Today, we're very happy to work with them, trying to explore new ways of innovation in the connected and automated vehicles.